faculty members and student invitees to this online talk on electronics beyond silicon. So as you know, we have been conducting these for the benefit of students and teachers uh, with the hope that they will pick up new topics, new ideas, new information that can help them in their teaching and research. So this is the easiest possible way of reaching our students and teachers. We cannot really conduct offline meetings nowadays because of time constraints and locations and all that. Since we have members from all over the Karnataka state, it would not be possible to meet offline. Very difficult also. So the easiest way is the online lecture series, online meetings that we have been conducting. And this is what one should really, the universities and colleges, they should be doing in what is known as outreach programs. Unfortunately, they are not doing. Universities and colleges, they're too busy with admissions, examinations, hostels, promotions, and all that. The academic matter has taken back seats, unfortunately, in most of the universities. Only selected research institutes like RRI, Raman Institute, and ICTS, IAA, they are doing these very nice outreach activities. And in fact, we have been helped by the faculty members from the research institutes in conducting these seminars. So, so I welcome you all to this particular webinar today, which will be delivered by Professor M.K. Rabinal, who is just recently retired from the physics department of Karnataka University. So he will speak for about 50 minutes on this topic and then answer answers in about 10 minutes followed after the lecture. So before he delivers the talk, I request our Joint Secretary, Professor Rudaswamy, to briefly introduce the speaker. Over to you, Professor Rudaswamy.
Thank you very much, sir, for this opportunity. It gives me an immense pleasure and privilege to introduce Professor Mohammad Hussain K. Rabinal, former professor and chairman, Physics Department, Karnataka University, Dharwad. He obtained his PhD in physics in the year 1994 from Indian Institute of Science, Bangalore. He served as a teaching faculty and then as a senior professor of physics in Karnataka University, Dharwad, from 1999 to 2025. He has been credited with many distinct research scientific positions and awards. Served as a research associate in Indian Institute of Science, visiting scientist, postdoctoral fellow in TFR, Mumbai. Served as coordinator for Innovation and Incubation Center and UGC SAP Center of Advanced Studies in Karnataka University and a member of Research Advisory Board of Christ University, Bangalore. Awarded to serve as a prestigious Commonwealth Fellow in UK for the year 2002 to 2003. Awarded with the prestigious Sir C.V. Raman Young Scientist by Government of Karnataka in the year 2013. Serving as a Fellow of Karnataka State Science and Technology Academy in the year 2022. He won awards several times for his best research publication by International Scientific Organization in the years 2010, 2015, 17, 18, 19, and 22. The prestigious publishing house, the Nature Journal, has highlighted his work on synthesis of fluorescent quantum dots in the field of nanoscience. His main current research areas are molecularly controlled electronic devices and synthesis and characterization of nanomaterials. He has at his credit 100 research publications in the Journal of International Reputation and delivered more than 100 invited talks at the national and international forums. With this brief introduction, now I cordially invite Professor K. Rabinal to deliver an important talk on electronics beyond silicon. Over you to sir, and thank you very much.
Thank you very much. Good morning to all of you. And I am thankful to Professor Rudraswamy for introducing me to you all. Before I start, I would like to thank Professor Kagli for inviting me to participate on this platform. keeping in mind of the all Karnataka State Physics Association teachers and students, I have made my talk a very fundamental level. So maybe at the end we can have questions, but in between also, if you interrupt me, no problem. I can try to answer. As you know, the title of my today's talk is Electronics Beyond Silicon. And well, this is the outline. I have put a couple of questions here. I probably I will be answering these questions in my presentation. Why we are thinking, beyond silicon electronics? What are these materials? The materials could be many, but I will not be able to touch upon many materials. But particularly, I would like to focus on organic materials, particularly in particular their organic molecules. I will tell you later on what I mean that. Then how to utilize them, how we can try to put them for electronics applications, I will try to touch upon, and where to use them with the specific examples. Particularly, I would like to take our own work, then try to show you that what one can do, and finally, the conclusion. Well, we all know silicon is a fundamental semiconductor, and if you look the semiconductor technology, more than 95% of the semiconductor industry, if you look, the silicon dominates more than 95%. And this is how we process silicon to convert from sand to silicon. It is a very simple representation, but there are many kind of innovative discoveries and technologies are involved. You convert sand to silicon, then you convert it to wafer of single crystal. Finally, you try to make electronics. This technology of silicon is so matured compared to other semiconductors. Today, we can grow single crystal of silicon more than the size of human beings. Just I have put here to just show you that a single crystal of silicon can be grown to very large size. Then we can slice them, make polished. Ultimately, we refer them as a wafers, and wafers are ready for making electronic devices. So the bottom part is the basic physics of this. This is a three-dimensional structure of silicon, and it has a wonderful structure because each atom is a tetrahedrally bonded because it belongs to a fourth group of periodic table. And because of this rigidity, silicon is wonderful material and very high melting point, boiling point. Therefore, the stability of silicon is very high. Then this is what the unit cell of silicon. And if I look the general properties of silicon, it is quite abundant because the sand is a raw material that is very abundant. Energy gap of silicon is 1.12 electron volt, very, very suitable with respect to the solar spectrum and for many other applications. Another parameter of any semiconductor would be field strength. What is the maximum electric field a material can carry? That is almost 1,000,000 of volts per centimeter, very reasonably high. Electron mobility is quite good, 1,400 centimeters square per volt second. Light to heavy doping, this is very important aspect. Any semiconductor, if we want to put it for any application, we should be able to dope it and convert P and N type. More importantly, you should be able to control the doping level. So that is well done in case of silicon and germanium, but silicon is much more. You can have N minus or P minus doping. You can have N or P doping, and you can have very heavy doping. That is N plus and P plus. It is really wonderful because any semiconductor you discover, you have to have this control. Hello.
No, please carry on. Some disturbance. Don't worry.
Another advantage of silicon is we can easily convert a small layer of silicon to silicon oxide. And this is very important because it will act as an insulator to create a gate. Therefore, it is a basic requirement for CMOS technology. Environmentally, silicon is very stable, very environmental friendly. Therefore, silicon is a wonderful semiconductor, what we have. Now that is not enough. We need to look, miniaturization of devices. It is a long way it is going, and still in future we have to look this. Here I would like to bring the statement of Dr. Gordon Moore, which he said in 1965. What you see here, the graph is a number of transistors in a IC as a function of time. What he said is the number of transistors per chip double every 18 months. That is what you see the solid line going on. And various Intel processing, numbers, you can see all of them more or less falling on that. That is how the rapidly developments took place. And today
Recording stopped.
extremely,
Recording in progress.
we are at extremely high level of creating devices. So finally, towards the end, he also said, I see that Moore's law dying here in the next decade or so, because by the time we had reached 14 nanometers is a device size. Today, when I look the lowest possible device that is created, TM image of that, what you see almost 10 by 10 nanometer kind of a transistor is created. But there are issues, important issues of power dissipation and other things. So, but we still want to go below this limit. Just to have a comparison, the original transistor discovered by first time, Shockley, Burden, and Bratton, that is here. This big chunk of a crystal is nothing but a transistor having 3 terminals, and today it has gone to very small size. This is a famous cartoon of Gordon Moore that is published in journal Electronics. And a cartoon depicts that there are various cosmetic and other shops, but there is also a person holding a small device and saying that one day computer will be handheld. So it amazed many people. That is what the cartoon reflects. But this has been converted to reality after the 60 years, 2025. Today, this is what our laptops, all of us, we are having such laptops, ultra books. And also IBM has created a very small kind of processor, and further this device can go to still smaller size. Miniaturization is not only important in electronics, it is also important in many areas. Always we say small is better. Here I have taken example of Newton. At the time of Newton, there was a refraction telescope, a very huge, and this is what you can compare with a human being. And Newton made a reflecting telescope by creating his own mirrors. In 1672, he demonstrated that this handheld telescope can do much better work what this refracting telescope does. And in fact, this discovery of Newton made him to enter the Royal Society of London. Now, why we are looking at materials beyond silicon is a very general one, and it is kind of a motivation. And what we are looking is, any material we think about, we have to look these functions. The material what we create should be more functional. Miniaturization should be possible, and a simple processable should be possible so that you can make a very large area materials and also devices, and also you can make the low cost. And another important component is a flexibility. We should have a flexible devices, large area, as I said. Abundance of material is very important because that is also one of the key parameters in deciding the cost. And low cost, this is not actually the least one, but it's a very important one because biocompatibility is a very important issue, because in coming years, we need to integrate electronics with human beings. Therefore, biocompatibility is also an important aspect. Just I will try to touch this one when one can realize how the cost is decided by which parameter. There are many parameters, but one of the parameter I'm taking the processing. What you see in this graph is electricity requirement joules per kg as a function of process rate, that is kg of material produced per hour. You can see the two solid lines as a boundaries, then you can see the data. So what you see here is energy required for inorganic semiconductors and vapor processing is quite high, that falls here. And if I take simple evaporation of metals like aluminum, iron, gold, etc., which we use in electronics, and this is a very high production rate and a low cost. But when you make electronics, it is mainly this regime that is very important because that decides the cost. So just looking at this graph, I would like to say the processing of high-end materials need almost 1 million times more energy than plastic and ordinary metals. Therefore, we have to look the materials which can be processed in this regime so that you can make the cost low. Now I will back to the organic materials as a general example. Later on, I will focus on very specialized materials in organic. So organic materials are very functional, and if I take this example, it would be very appealing to look all of you that why organic materials are important. What you have first as a benzene, you have structure of benzene. In the real form, it is a liquid, and I can call approximately I can call it as optical band gap, but it is not optical band gap. We refer it as a homo-lumo level separation. That is a 5.8 electron volt. Next, if I take the two benzenes joined side by side, you create a naphthalene, and it is a solid material. It looks a white solid. And naphthalene balls are very known to us. We all use. And the optical band gap of that is 4.3 electron volt. Further, if you extend this by taking benzene 3, you can join them 3 together. You can have anthracene. Again, it is a white material, but not as white as this. You have optical band gap 3.25 electron volt. Similarly, I continue to 4. What I create is a tetracene, and the color of that is more brownish. You have a 2.6 electron volt as optical band gap. Then I go to the next one, that is a 5-membered pentacene, black, dark colored material, and optical band gap is 2.01 electron volt. And it is a best organic semiconductor, many wonderful labs, they have dedicated their efforts to create this material, and characterized doping and other aspects have been studied. And further, you can continue here, you can call it as a polyacenes, and you can bring the optical band gap 1.18 electron volt. That's very close to silicon. So this is a functionality of organic material, which is not there in case of inorganic materials, because in case of inorganic materials, you have a fixed properties. But in case of organic materials, simply by joining, by creating conjugation, you can create very interesting materials. This is just a side example when you create the bio or organic materials with inorganic material. Here is example of carbon nanotube coupled with the protein, and the protein has many wonderful configurations. Here are the two examples, folded state, unfolded state. You can create the many minima and metastable states are possible. That has been depicted here. You may be wondering how it is related to a material scientist. By having this, you can try to explore this in electronic devices, and these minima, multiple minimas of this composite, can be utilized to make electronic devices. I will come to this later with respect to DNA. Processability of organic material is very simple. What you have is a substrate hot plate. You can put a plate. You take a liquid of organic or nanomaterials. You can just try to put it. You create a film. So in fact, it has gone much beyond very simple thing. You have here example of a liquid and a pipette. You can try to control the condition of this. You can try to have assemblies of nanoparticles and also organic materials. As I said, one of the other parameter what we need to look is a flexibility. Organic materials can give you this kind of flexibility. You can have, foldable mobiles. You can literally make it almost 360-degree bending. Nothing happens. And such devices are already entering into the market. And of course, if you make the things with organic materials, you can try to have very flexible stickers. You can integrate that on a human body. Large display, that is what you see here, very huge, probably about 20 by 20 feet, which is not possible with inorganic materials, but it is possible with the organic materials. Well, abundance and low cost also go together. And this is a cartoon I have taken from one of the review article. What it says, burn a candle to collect soot and make computer. Our material production should be so simple so that we can try to explore them for the modern electronics. As I said, biocompatibility, it is very important. Whatever electronics we make, we must be able to integrate to biosystem. Here is just a cartoon taken from this paper, and it is a green electronics. Not only to plants, you can also think about integrating electronics with human beings. But ultimate goal of organic electronics is, can I catch just a single molecule like here? Then you have electrodes and have a gate so that you can try to make the field effect transistor and try to push the charge carriers across this molecule and try to see the discrete conductance associated with the molecule. Well, now I will come to the second question, what I said in the beginning in outline, that is utilization of organic materials. How do we utilize them? Of course, there are various ways of utilizing these materials, but I'm putting them in three broad classifications. One is you can try to create a thick material of organic so that you can have electrode bottom, electrode top, then you can put material. You can think about making electronic devices. Another possibility is you can try to have very thin deposition of organic material on electrode. Then you try to make devices what we make in case of silicon and germanium. But there is another very special class of using or utilizing organic materials, that is extremely thin films. A film of just a few atomic thick. And in fact, that has been depicted here. You can have a semiconductor or a metal. You try to control the chemistry so that individual molecules can come and just attach. And what you have, the thickness of organic material is just one molecular layer thick. Therefore, such materials are referred as organic monolayers, and organic monolayers are very interesting class of materials. And in this presentation, I will be focusing on this aspect because for last 15-20 years, I have been working on these class of materials. Well, this is a kind of a basic cartoon of utilizing organic molecules to create just monolayer. What you see here is a head group, the one which binds on a given material. Then there is a tail of a molecule. This all depends upon the what kind of molecule you are choosing. Then at the end, what you have is a functional group. In fact, you can create a multi-layers of this. You can create the R group so that you can make more functional materials. Well, this is when a monolayer is created on given material, then there are various ways of binding. And this is a cartoon we created for our recent review article, that is here, SES Energy and Fuels. Just it depicts that a metal or a semiconductor as a core, you can try to bind organic molecules on that by various means. One is van der Waals interaction, what you see, delta plus, delta minus. A weak interaction can be created so that the molecules can bind to the given material. There can be covalent bonding. In a covalent bonding, the metal or the semiconductor will give one electron, molecule will give another electron. You can have equal sharing of electron, therefore a covalent, very strong bond can be created. There is also possibility of electrostatic interaction, a complete transformation of electrons so that you can have ionic bonding. And one more strategy, that is a coordination interaction. It is a kind of a lock and a key kind of a molecules you can design so that you can try to bind them on various materials. This is just to appeal you that how important is the organic monolayer research. It is just a figure created by us for the review article. What you see along y-axis, number of publications as a function of time. You can see this research originated just at 1985. Of course, there were small number of papers which are not visible here. It has become significantly important at this point, and it goes like this: number of papers per year rapidly gone to large number. And what you see here is important discoveries. For example, here you see studies on molecules and SAM self-assembled monolayers on solid was started here. Semiconductors, metal surface modification using organic molecules and creating moltronics that begin here. Then you have a molecular tuning of electronic devices. Conventional electronic devices you can tune by designing molecules and attaching. You can create a smart sensors. Then you also see that organic monolayers have been utilized for other conventional applications, that is solar cell modification, then molecular electronics, and also a new area that is a memory stir. I will come to this later. And finally, you can see presently the organic molecule designed interfaces can be put for water splitting, energy storage, etc., and many more. Therefore, the monolayer creation on a material, just a one molecular layer thick, have a very, very important role in modern science. This is just a history of organic monolayer. It is not a new. In fact, it starts from 1750. Benjamin Franklin reported that a few drops of oil on a tank can spread to very thin layer. Here is an example. Always you can see this on a roadside. Whenever in a rainy season you see oil is spilled on a road, that is oil spreading on a water. On a road, you can see beautiful pattern. This is nothing but that pattern only. And this is just happening because the oil spreads to very, very small thickness. And you can also see Pockel's experiment in the kitchen, who tried to conduct such experiments. 1890, Rod Rayleigh continued and repeated Benjamin's experiment, and he measured by optical scattering that the thickness of such oil is extremely small, just one molecule thick, very simple, you can create in a very simple way. Langmuir is a very known person who introduced the concept of this to 2D materials. And also Catherine Blodgett. We have today Longmire Blodgett trough to deposit such materials. And Langmuir got a Nobel Prize in 1932 for his work on these monolayers. And finally, this field entered into nanotechnology. And today, along with the nanoscience, we can make many materials design using this technique. This is what the Benjamin Franklin did. You have a water, put a little oil, it spreads to very small thickness. And this simple experiment or idea has been converted into experimental technique. You can have the one liquid, say it is a water, then oil, you can spread very thin, then you can have a substrate, then you can have a couple of, you have this electrobalance. It will try to push computer controlled. You can try to make the monolayer compact the way you want, and then finally it can be pushed on this. This can be slowly pulled so that various materials can be just deposited on given substrate. The modern, the LB trough looks like this and quite expensive, but it does wonderful job. Later on, a couple of other discoveries were also made. Gisman, 1946, surfactant monolayer he created by a very simple setup, and Sagiv, self-assembly of alkane silanes on silicon oxide. Alaro and Nuzo, they could able to put alkane thiols on a gold and silver surfaces. Well, the foundation of monolayers, you can deposit them on, because they are very thin layers, because as I said, only one molecular thickness. And very interestingly, you can deposit them on a wide range of materials. You can deposit them on metals, semiconductors, polymers. In fact, if you ask me, they can be deposited on any material. Now I will come slowly to our work, what we have done. Therefore, I have taken example of silicon once again. Already I said, this is a unit cell of bulk silicon. Now, if you see the silicon, as I said, we can grow that into a large size of crystal of a different orientation. In fact, you can grow the silicon with a different orientation. You can have 100 facet, 110. This is how it looks like. You can have 111, 112, and many more. If I take silicon and try to slice in a different direction, you can have a different kind of a surface. I will back to that here. Then what is more interesting is this is a typical silicon material. Inside you have the bulk bonding. Every atom of silicon is a fourfold coordinated. But once you come to the surface chemistry is different, because if I take the atoms which are sitting on the surface, they don't have any bonding here. Therefore, they are more susceptible for oxidation or attachment to any of the atoms or molecules. They come from the air. Therefore, you have a very interesting substrate to engineer, because if you look at more closely, we can do many things. And finally, what you can see atomic level is you have the dangling bond. This is called a dangling bond because it is a hanging bond. Nothing is there, and it is susceptible for any kind of a chemical bonding. Therefore, you also create a dipole moment because of non-uniform distribution of electronic charge. Once I come to here of different surfaces, silicon 100, this is how it looks like. In fact, you have the size or separation. This is a 110 surface, and this is 111 surface. Now it is atomic level physics. When we look the surfaces, they have a different kind of a topology. Therefore, they can be studied and explored for interesting effects. Thanks to high-end the scientific discoveries and technologies what we have, these are the images of scanning tunneling microscopy. You can have atomic resolution under very clean condition. So if you record the surface topography of 111 silicon, you can see clearly atoms of silicon very well, and sometimes you can see some defects also. This is a real surface of silicon, and similarly one can see 100 surface also. You have very clearly what I showed in a previous slide. Such kind of predictions are existing, and they also get modified under given conditions. We refer that as a reconstruction of silicon surface under different conditions. Well, that is a very high level research because you need to have very high-end facilities. But what we did at Karnataka University is a very simple kind of a research in a similar line. And what I try to show you that you can have very simple facilities through which you can try to do similar work. So other methods of monolayer deposition, you can think about a simple beaker. You have a solvent, you put a molecules which you want to deposit, then you just put a plate inside for some time, maybe for a few minutes or a few hours, that it will be a self-assembled molecules, just they go and bind to surface, and what you have is a monolayer arrangement. And this is at no cost. It's a very simple kind of experiments one can conduct. So if you look this, what are the ways one can deposit monolayers in a very simple way? I have quoted a couple of them. One is called a chemical reaction method, Grignard reagent. Here we add metal salts to happen this reaction. Another is electrochemical deposition. You can try to apply electric field provided your molecule can be guided under electric field, so that electrochemical deposition are also possible to create monolayers. Another is a photochemical. Just to shine a light, the reaction happens because the photons will supply the required amount of energy for breaking and creation of chemical bonds. Another possibility is a thermochemical. Just you heat the solution for certain temperature so that you can have a deposition. And little advanced level is chemical vapor deposition, but it is not very simple one, but you need to have facilities to do so. How this happens? This is what the case of silicon. If you take a silicon, what is shown is a silicon surface hydrated. In a just a chemical treatment, you can create a hydrogen bonded silicon. Then you can have free radical, as I said, Grignard reagent, and you can also heat simultaneously to 170 or whatever temperature, so that the molecule, what has been taken to create a monolayer, is not just any ordinary molecule. You need to take alkenes and alkynes. Alkenes means at the end you have a double bond. We call it as an unsaturated molecule. Similarly, one can go to alkenes. You have a triple bond. So such molecules are unsaturated. Under very small mild condition, you can trigger them to open up their bond, and they can go and bind at this place. And finally, you can try to have the molecules bonded to silicon surface. this is how this technique of deposition has been studied by others. Scanning tunneling microscopy. I don't have to tell how it works because you have the scanning probe, just one atom sitting at the end, one atom from the surface. It will measure the tunneling current, and finally it will construct atomic resolution of a surface. So a bare silicon looks like this, and 1,5-cyclooctadecene is a molecule, as the ENE indicates, it is having a double bond. Then once this molecule gets deposited, you can see this surface changes to this, and literally what you see here is each bump is nothing but a molecule deposited on that. Similarly, this lady is very famous. Gillian Burek worked a lot on such materials. It is a dynamic monitoring of self-assembled monolayer formation on a silicon by simple chemical route. What I said in previous slide, you have a silicon hydrated, you attach this molecule goes and binds. What is more interesting is these pictures. In a 3 minutes of deposition, you can see silicon, and what you see, a small percentage of molecules deposited. 15 minutes, you can see more deposited, 30 minutes, and finally 120 minutes, you can see complete coverage of molecules on a silicon surface. So it is wonderful that we can look by doing dynamic monitoring by scanning tunneling microscopy. One can study the bonding of monolayers. This is another example to characterize when I do such reactions, whether molecules are bounded or not. This is about X-ray photoelectron spectroscopy. What has been depicted is a basic principle of this technique. You have valency band, conduction band, Fermi level. Say it is a semiconductor, metal, then vacuum level. It doesn't matter what material, but what we have, discrete atomic levels, K cell, L cell, M cell. Further in that, you can have the electron sitting in 1s and p states and all that. What this technique does is high energy X-rays are sent to the material, and energy is so high that it will knock the innermost electrons. And once the electrons are knocked, they will come out as a photoelectrons. Then one can measure these electrons and try to create a spectrum. What you have is a signal of photoelectrons as function of binding energy. So binding energy is a specific to every material. Therefore, by measuring binding energy very accurately, one can find out what is the chemical composition of a surface. To highly precisionally one can measure it. Here it is just an example. Cartoon is created by ourselves for the review article, just to give a feeling that how this technique can actually sense. Suppose you have example of this molecule and there is a silicon. By chemical reaction, you have bonded this molecule. There is a carbon and silicon bonding. This molecule has a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbons. At the end, you have oxygen. There is a fluorine. But if you look carefully, there are, these carbons are sitting under different conditions. Chemical environment is different for these carbons. For example, this carbon is bonded to silicon. It has a 1 environment. Therefore, it is marked as a yellow. Then if I go to this carbon, this side it has a single bond, this it has a double bond. Therefore, this carbon is again different from this carbon chemical environmentally. Therefore, I have marked this as a green carbon. The remaining 1, 2, 3, 4, 5, 6, 7, 8 carbons are sitting in identical chemical environment. And if I go to this, again it is sitting in a different chemical environment, because this side there is a carbon, this side oxygen and a fluorine. So now if you record this XPS spectrum of the carbon, what you see is suppose carbon in a free condition, you're supposed to get a dotted line, and this carbon, which is sitting in a highly strained environment, has a more binding energy. Therefore, it appears here. And this carbon will appear here, and this will appear here. Therefore, by a shift in the position of the binding energy, one can precisely tell the how it is setting and what kind of chemical bonding it is establishing with respect to a given substrate. Similarly, one can record the spectrum of oxygen. With the ideal, it is shifted to this side. One can also record a fluorine, which is here, got shifted as compared to its ideal. Therefore, By recording such spectrums, you can precisely study the monolayer formation on a given material. This is again a very interesting picture, of course computed, but it has been recorded also. It is a copper phthalocyanine and one other organic molecule together deposited on a silver 111 surface. You can see the beautiful pattern just like a tiles. In fact, that is how the atomic level science we can do in material science, particularly monolayer formation. We can deposit the materials that we want so that we can create more and more functional materials. And here is electron diffraction pattern of such monolayers created. Well, the second question comes to our mind. We are talking about very, very thin atomic layer bonding on a given material. Are they stable? Can I do the electronics? Can I create devices which are stable for more time? So that is a very important question. And in fact, it has been studied long back. You can see a paper in 1995. What you see here is XPS spectrum of a silicon, bare silicon. Okay, suppose if I have a bare silicon in a pure condition, then I should have only one peak like this. Since we know that the bare silicon is not stable because it is having dangling bonds, immediately it reacts with the atmospheric oxygen. Therefore, a small layer of oxide is always created on silicon. Whenever we use a silicon, we try to etch it so that we can remove the oxide layer of silicon oxide so that you can utilize the material. What you see here is once you take a silicon, create a clean condition, leave just for a few days, you can see the oxidation peak that is coming out. And here it is a typical spectrum recorded by these people. And what they claim is within few days, silicon will have a silicon oxide of 10 angstrom, and it is a self-limiting process. Probably it will go to 10, 50, 100, then it will limit, then it will act as a protective layer. There will not be any further oxidation. What is more important is overlapping along with this is a blue line spectrum. And these are the molecules which were bounded on a silicon by these groups. And then they recorded the spectrum. They don't see any oxidation. It means the passivation by organic molecules is so perfect. These molecules do not permit oxygen to come and bind or convert silicon to silicon oxide. Not only that, very interestingly, they taken such interfaces. They boiled in CHCl3 for 2 hours, boiling in water for 7 hours. Then they left in open condition for 11 weeks, months together. They do not see any oxidation. That is the stability of these monolayers. Another group also demonstrated the stability of various monolayers. It is a cartoon of that. What you have is a substrate. You create monolayers of various kinds, which are written here. I will not go into them. Not only for a silicon, they have done it for silicon gold, silicon carbide, chromium nitride, silicon nitride, silicon oxide, indium tin oxide, and many more materials. What they see is once they are created, you try to vary the condition. pH going from 3 to 11 is very harsh condition. pH 3 is acidic, pH 11 is highly alkaline, and even then nothing happens much, but still monolayers are stable. Molecules are stable. Similarly, you can heat the material to check the thermal stability. Ranging from 25 degree to 600 degree, monolayers are quite stable. It means what simple materials we are talking about, they can be put for a harsh conditions and we can make electronics out of these interfaces. Well, just I quoted many applications possible for such monolayers. I'm just giving some numbers here, but there can be still more. Such interfaces can be used for surface modifications, surface optoelectronic properties, microcontact printing, chemical passivation of semiconductors. Just previous slide, I showed that molecularly controlled semiconductor devices, Schottky junctions can be modified. We can actually create a platform for molecular electronics. Molecular memory devices, I will be touching upon this later on. Molecular dielectrics, because some of the molecules are having very good dielectric properties. One can actually have the gate materials and interfaces for solar cells, functional surfaces for chemical, bar biological sensors can be created, and nanomaterials functionalization also can be done by this. So just to have a feel about this I have taken from the literature. how the molecules can modify the surface photoluminescence of gallium arsenide, very well-known semiconductor. What people have studied is how the surface attachment by organic molecules can they affect the surface photoluminescence. What you see is a bare, just etched gallium arsenide. You have the photoluminescence signal up to this. By putting various molecules, you can try to tune, and finally you have the aluminum gallium arsenide. It is alloy of it by putting aluminum. It is at wide range of stoichiometries it forms. So you can move from this photoluminescence to up to this. If you look here, almost it is a 3 orders of magnitude photoluminescence signal can be modified simply putting various molecules. And it is again from a review where somebody has reported how the molecular electronics can be very, very important. And it is a cartoon. You have the organic molecules locked. You can see molecule locked between two electrodes. Then you can actually, you have a compressed condition here. Here it is a stretching condition. Again, you can have, just try to make it compressed and elongation. But doing so, if you try to look the current voltage curve of that, you can make a same molecule to act like a tunnel diode, backward diode, even simply a registrar. It is quite beautiful, You can just create one molecule by inducing stress. You can create, diode, register kind of a behavior. Well, I will come back to our path, what we did for last 15, 20 years in this area. Of course, more than this, but just I want to quote 3 examples. One is a molecular junctions, another is memory stress. Finally, very recent work, how we can put molecular modification for a zinc air batteries. Formation of molecular junctions, it is, gold surface is shown, molecules you can create, then you can try to have a contacts. The molecules of different kind can be locked between the electrodes. It is a very, very tricky and very, very delicate work. You have to do all this without damaging the molecule so that you can try to measure the device property. Well, this is actually all these techniques of measuring molecular modification have gone from our lab. We, during the last 15, 20 years, as I said, when we were working, we had a great challenges how to make the molecular junctions. Every time we could able to find a new way of making. This is one that is in a Review of Scientific Instrument 2006. Then further another technique of measuring, even putting a light from the bottom so that you can try to shine light and see the photo response of the molecules. Another way of making molecular junction by taking mercury column. This is a multiple contacts. In fact, you can lift the contact and float on the surface because we cannot do thermal evaporation. If you do thermal evaporation of the top contact, it will go and damage the monolayer. Therefore, you cannot have the response of the molecule. Further, we extended that to the by some other means, and finally, we also had putting ink into the pads and creating monolayers. And these are the properties measured and demonstrated that such a simple method of lift and float multiple contacts can work. Further, I will show you later on. We have another very simple technique. It is very, very simple technique to make a large number of contacts on a given molecular junction. This is what it is. It's a very recent work, 23. What we showed here is you can create a molecular junction for biological molecules or organic molecules, simply floating a paper. You can float so that you can create a junction. This is what the concept. And such kind of contacts are available in the market, maybe 100 rupees, a very big seat. You can get about 1 meter by 1 meter for 2 to 300, which has these created dots. There is a sticker material. You can simply lift and try to float. So what we have shown is, this is what it is. There are 2 directions to this. One direction this way, another is this. Let us go in this way. You can take this contact. This is what you have. You have a base material and it can be lifted easily. There are holes inside. Now you take the ink of conducting, that can be silver paste, or you can also create your own ink, or it can be carbon paste. Simply you drop so that the gaps can be filled with this ink. Then once it dries, you can lift it. Now back to here, I can take a material. We have demonstrated this on an indium tin oxide glass, conducting glass. We try to deposit DNA molecules on that so that you can have the deposition of DNA under UV light exposure. It is a photo deposition. Then you have a substrate and try to lift it and simply put and apply little pressure. You can create a molecular junction. This is what it is. What you see here is ITO. Then once DNA is deposited, it will become slight, grayish. It is not very clearly visible here, but you can do electrochemical deposition of a DNA or a photochemical deposition of DNA. Once you constitute this device, you have the bottom ITO as a bottom contact, then in between DNA, then you have a top contact. Basically, you are creating this kind of a molecular junction. And what we measured, current voltage, this is how it is. It acts like a diode. DNA shows diode-like behavior. And what is shown here is almost 50 cycles of recording. It is a quite repeatable. You can have a very, very simple approach to make molecular junctions. Well, molecularly controlled electronic devices also we use to control the Schottky junctions, that is the semiconductor metal junction. And we had chosen a couple of molecules, series of molecules. And at the end, what you see, triple bond. These are unsaturated molecules. Idea of choosing these, you can easily bind them on a given substrate. Then we have the choice of variation of functional groups. You take this, then you have a bromine substitution here. This is a molecule at the end. Again, you have triple bond. Here, chlorine is substituted. Similarly, nitrogen is substituted inside the ring. By doing so, you can try to vary the dipole moment. We wanted to know what is the effect of dipole moment once you create such monolayers. Then we created dipole moments. You have a molecular attachment here. If the dipole moment is going outside the surface, that is from negative to positive, we call this as outgoing dipole moment. Similarly, you can deposit some of the molecules where the dipole moment hits the surface. What is the purpose of this? Because once you assemble large number of molecules in this way as a monolayer, it will modify the surface property. Therefore, you can have a variation of band bending of a given semiconductor. So what is more interesting is here, current voltage curves of various molecules. You can see it is a forward characteristics of a silicon molecule, a metal contact. You can literally tune, depending upon the dipole moment, you can literally tune the current voltage characteristics. And this is an effective barrier height change as a function of dipole moment. You can tune the barrier height to large extent. Therefore, the molecular modification of Schottky junctions is a very important approach to design a new molecular electronics. How this varies and all we have written here. That is what tells the dipole moment is an important parameter to control the change of surface voltage, or you can say the barrier height. Again, these are very simple small molecules we tried on highly conducting silicon surface, and different types, dipole moment going this way, this way, this way. And what you see, without molecular contact, without having a molecules in between silicon and metal, it is just like a shorting kind of contact, because we have taken P plus silicon. As I go to different molecules, I can literally change. I can make a ohmic to diode like a behavior. And in fact, these are the curves which will tell what is the mechanism that is happening when you try to push electrons across such interfaces. We have done even other works, but I will focus on one important aspect there. And that is what I'm trying to do now. It is a very, very basic physics. What you see diagram here is you have a N-type semiconductor. There is a valency band, conduction band. You have a metal contact. Then the Fermi level of metal is here. So this is a vacuum level. So what I have is the work function of metal, amount of energy required to remove electron from here to this level. Similarly, same definition applies to semiconductor. And this semiconductor has an energy gap. So without bounding condition, what I see is a Fermi level of metal is here. The Fermi level is of semiconductor is here. If I make an electronic contact between these two materials, if you establish physical contact, the Fermi level has to equilibrate. The Fermi level has to be equal throughout the material from semiconductor to metal. Therefore, this is what happens. When this happens, there is a band bending at the semiconductor. That is what it has been shown. Now, if you look, you create a barrier height, and this is what we measure when we try to push electron through such interfaces. Now come back to this height. This barrier height, what I showed you now, depends upon the contacting metal. If I change contacting metal, I can choose metals having a different work function so that I can try to move them. If I do so, I should be able to vary the barrier height. So theoretically speaking, this is a very simple equation that predicts how barrier height varies with respect to electron affinity of the semiconductor or a metal work function. What you see is a theoretically predicted line should go here. As I change metal of a different, like gold and silver, I should be able to vary the barrier height. So what is the reality, experimental reality? Experimental reality on silicon is when they took aluminum, titanium, nickel, etc., there is no variation of the barrier height. So for a long time, it was a big question, and later people came out with the idea that the barrier height doesn't change when I change the metal of a different work functions. The reason for that is we have not taken in this band diagram, we have not taken the effect of surface states. If I take the surface states into account, then only I can explain why there is no sensitivity. And of course, if you don't control surface states, nothing can be done. Therefore, this is referred as a Fermi level pinning, and this is what we try to attempt by creating molecules at this interface. So this is a concept of our work. What we did is there is a semiconductor, silicon atom. You have a molecule. You can make molecule to bind covalently. Then I change the contacting metal. I can go from aluminum to gold. If I do so, I can change work function to almost by 1 electron volt. Aluminum has a low work function, whereas a gold has a large work function, almost a difference of 1 electron volt. So now if I try to draw the band diagram of p-type silicon and also taking these metals, for example, this is for a gold, this is for aluminum. Don't worry about this energy band diagram. What is take-home message? I will just tell you that. So what we have done is we have put the gold here with the work function, then the vacuum level, p-type silicon, and of course the molecular levels. And what I expect when I put the gold on a silicon, I expect p-type silicon and gold, I should have a low barrier height. But if I go to the aluminum or p-type silicon and again do the same thing, then what I expect is a large barrier height. So it means if I take aluminum and p-type silicon, I expect a large barrier height. And if I take a gold and p-type silicon, I expect a low barrier height. So if I do simply taking a p-type silicon and gold, p-type silicon and aluminum, try to make Schottky junctions, and I expect a large barrier in case of aluminum, and I expect a low barrier in case of a silicon. I will back to that point. But now what we did is we took a bare silicon, created devices, which is I call unmodified. I don't put any organic molecules. I try to measure different junctions, same semiconductor, same material. I am creating multiple junctions, small dots. When I measure from dot to dot, I can see unmodified, there is no consistency. There is a variation, large variation in current voltage. But however, if I modify, I can again measure from different junctions. I can see repeatability is quite good. The molecular junctions are going to create more stable and homogeneous devices. Now again, it is a little complicated. I will not make you to put more efforts to understand. What I'm trying to tell you is that what you see, the red curve, that is the current voltage curve. Similarly, a red curve, current voltage curve, that is modified by putting molecules. What you have black is unmodified. Without molecules, if I do the dark curve, for this is a case of gold, and this is a case of aluminum. If I don't put molecules, I don't see any change of current voltage curve of gold silicon contact or aluminum silicon contact, that is a dark. But however, if I put organic molecules, I can open up. I can see a low barrier height in case of a gold and the same more barrier height in case of aluminum. So it means the organic molecules can passive at the surface states and try to open up what is expected theoretically, that the barrier height of the semiconductor metal junction should vary with respect to change in contacting metal. Then I come to the second aspect, as said, memory devices. Probably, sir, how much time I have?
Yeah, another 5 minutes or so. Maybe.
Okay. Yeah, I will try to give a just glance. Now there is a new kind of a device. You all know the resistor, capacitor, inductor, but one here it is missing, this quadrant, that was discovered in 1971 by Leon Chu. We call it as a memory device. It is a memristor. It will switch from conducting to high conducting to low conducting. This is how, and this can be a good memory, and a lot of many papers are coming up in this direction. So what we have done, we tried to explore DNA nanoparticles to create memory devices. This is a banana. You can do simple processing. You can have enough DNA. This DNA can be made as active material for electronics. Well, this is all basic. DNA is made up of, sugar and phosphate group. Then you have in between adenine, thymine, guanine, cytosine. There is a particular link. You can have a DNA, and the DNA is available in almost every material. What we made is we combined DNA and lead sulfide nanoparticles. You can see nanoparticles of very, very, very small size and very homogeneous. When we make the composite of this by electrografting, you can create a composite film of that. And this is what we did. We put lead sulfide DNA composite between two electrodes and try to measure the current voltage curves. It is not like a resistor. While going, it will go to high conducting, switches to low conducting, goes here. You can see arrows, again comes back, and in the reverse again comes back. Now, this is a kind of a memory device, a memristor. 50 cycles of repeated and no deviation. Of course, there is a variation small, but the phenomenon is very repeatable. To explain this, we have proposed a energy band diagram to explain what is happening there. I will come to the last aspect, that is the metal layer batteries, and what we did using molecular modification. Just I will try to highlight. This is a metal layer battery, very new generation battery, not like other batteries, very benign, nothing happens, no explosion, because it eats oxygen and maintains the power storage. That is what it has been given here. And it is of very low cost, energy density is very high, and you can make aqueous, non-aqueous batteries. And again, this is the figure I showed in previous slide. Well, a couple of issues are there around these batteries, that dendritic growth, surface passivation, metal corrosion, hydrogen evolution. These are very serious issues. We need to work on them. There was a review article written by us on these aspects, metal layer batteries. And what we made, I will try to tell you. So what you need in a zinc air battery is very large surface area is required in order to have a good battery. We have a zinc plate. We wanted to deposit zinc on that to make a zinc air battery, but we created organic monolayers and then we try to deposit. What we found is we can deposit very large area zinc nanoparticles by doing so. You can see chemically unmodified zinc deposition. Once you modify with the molecules and deposit, it becomes more dark. But once you look the SCM images without modification, this is how. With modification, you can see plate-like growth. So it becomes surface area becomes more. We combine that with the cobalt oxide cathode, very simple deposition. Finally, we made a batteries. And in fact, we have advanced level of quad design, but here the discharge them. Well, I have come to the end. Organic monolayers are important materials, molecules on semiconductor. You can create highly functional interfaces. It helps to tune conventional electronics, molecular electronics. You can have molecular memory devices, many more you can have. Functionalization of nanomaterials, also another thing, molecules can be utilized. Design of specific chemical and biological sensors can be created. It's only just limited. Many more can be done. Many things are possible, and that is happening. So this is just my acknowledgement to former students. Even some of them also completed. Only Rachana is working now. She is working on triboelectric nanogenerators. Just by rubbing, you can collect the charge and have the small power generation. Otherwise, other students, they have completed and joined elsewhere. Thank you. Thank you very much.
Oh, thank you very much for a very interesting and very informative talk. Now, there's time for some questions and comments. Anybody
Yes.
would like to ask any questions or comments, they can do so. Yeah, please ask the question. Okay.
No, I showed you real life examples only. From our lab, we made a memory devices. We made modified zinc air batteries to have better efficiency. You can refer our paper. You can see that you can make what I showed you is a LED burning with our own lab metal air batteries. Okay. Well, what I showed you, one place I showed you that the stress also can make molecules to act as a resistor and a diode. Probably for real application, it may not be, because those experiments are done with atomic force microscopy and scanning tunneling microscopy. Still, they are at lab level, number one. Number two, what I showed that by putting molecules, you can try to change the charge transport properties of Schottky junctions. Yes, it can be converted into real applications.
Sir, good afternoon. Yes,
Wait.
please.
Okay, ask.
Yeah. Yes, sir. Good afternoon, sir. Wonderful presentation. Sir, I have that question regarding DNA banana peel you have done, sir, with nanoparticle. So,
Yes.
are the curve which you have shown, those are CV curves, sir, or something
No,
else?
no, current voltage curves. They are not CV curves.
They are not
Current
CV curves.
current voltage curves in a dry condition. There is no electrolyte there.
Okay, okay.
So
Yes.
let me tell you what we have done. We have made lead sulfide nanoparticles.
Okay.
Then we put into solution. Then we have a DNA, make a composite material, deposit, dry it, then make a device.
I have a simple question. How uniformly you can deposit these organic molecules onto substrate, and how do you check the uniformity?
Yes.
Uniformity.
Yeah, it's a very important question, but we can make highly uniform because we have an optical technique of measuring thickness that will tell us whether the molecule is uniform or not. But generally, after deposition, they are thoroughly washed and rinsed. If there is non-adherent material is there, that will go off also. But we have optical technique, ellipsometry will tell you whether the thickness is uniform or not uniform. But if I say it is a monolayer, it is highly uniform.
Are there any examples of circuits being made with these diodes and all those devices that you have thought about? Any circuits being prepared?
Yes, we made the circuits in our lab. Circuit in the sense, not a large scale, but
Yeah.
not a kind of, but it can be done. In one case, we can make a circuit. For example, I said a simple sticker can be taken, contact, you can lift and try to float. Then you can connect. You need to connect to other circuits, but it is only a device configuration.
Devices.
Suppose I want to connect my device with a capacitor, resistor, then it becomes a circuit.
So connections are possible. You can make
Possible.
So any other questions?
Sir, we are doing that experiment EC of copper. Can we say that the material deposited on the copper plate, on cathode plate, is nanomaterial?
I couldn't get your
You got my question? I don't know.
Can you
Repeat.
Sir, normally we are doing the experiment EC of copper in physics. Huh? So the copper, will be deposited on the cathode plate. Okay, we put the copper plates connected to the battery. One is to the negative and the other to the positive.
Yes.
And copper, we normally pass the current for about half an hour. And copper, we put it in copper sulfate solution. And copper is deposited on the cathode plate. We can see that. But my question is whether we can say that it is a nanomaterial.
Exactly. You can do that. Actually, what you have to do is you have to see, look, if you are depositing nanoparticles of copper on copper.
Yes.
If I do X-ray, then base plate also will contribute in XRD. One possibility is you can scratch that material.
Uh-huh.
Then you do the XRD, it will tell whether it is a nano or it is a crystalline material.
Oh.
But people
Yeah,
have
that
done,
entire plate has to be sent for characterization.
yeah, but there is issue. If you send the entire plate,
Uh,
the X-rays will go to even bottom plate and come out.
oh,
So you have a contribution of substrate and also the top material.
oh,
But if
oh.
the top material is very thick,
Mhm.
then it is only of top material. Then you can say material is a nano or not.
Mm. Okay, thank you.
I have another simple question.
Yes, sir.
You said that you can select, let's say, 100 plane, 111 plane. Is it how is it possible to select one particular plane in a
Yes.
crystal?
Yes. It is,
Experimentally, I'm saying.
yes, yes, yes. It is a very well developed technology. Like, let me tell you first what we do.
Ah,
It is a very unfortunate to mention here. Till today in India, there is no company which makes a single crystal silicon.
ah,
Okay, number one. We always purchase from China, America, France, or other countries.
mm,
But the technology is so matured, when they grow, they will put a particular seed of particular direction.
mm,
When the crystal is grown by various
ah,
techniques of crystal growth,
ah,
they grow in a given direction only.
ah,
When I get a rod, what I showed beginning, then if you slice that,
ah,
it for sure that the face of that is 110 only or
ah,
100.
ah.
Today, when we ask a company, it will ask us, would you like to have 100 or 111?
Ah,
So they supply. But technology is very matured.
ah. Very good.
In future, do you think silicon is replaced by other organic materials for electronic industry?
Already it is
Silicon?
happening. Already such materials have come, devices have come, displays have come.
Huh.
But
Even performance wise, it is same, silicon can be replaced, by other material
see, it
as
is
far
not
as.
like we don't want silicon or we want completely remove the silicon.
Uh,
We want to have a silicon wherever it is necessary.
uh,
But the more, for example, let me give the example of, one main drawback of silicon.
mm,
No doubt, 95% dominance is a silicon in a semiconductor industry.
mm,
Silicon is an indirect band gap semiconductor.
mm,
Suppose I want to make a light emitting diode out of silicon, I cannot make because it is not a good material.
mm.
For which you need to go for other material which is having a direct band gap.
Okay.
Similarly, suppose I want to tomorrow have my TV as a kind of a calendar, I can roll it.
Mm.
Very, very big size. I cannot have silicon. Then we have to go for such materials. But already replacement has started. In silicon, not that we don't want silicon. Silicon will sit wherever we need to have. We should have other materials.
Okay.
I hope I answered your question.
Yes, sir. Thank you. Thank you very much.
Okay, if there are no further questions, I request our General Secretary, Professor Nagaraju, to propose a vote of thanks.
Thank you very much, sir. In fact, you have covered a lot of material on the preparation of nanomaterials. Am I audible?
Yeah,
Yes,
it's fine.
Oh,
Yes,
yes, sir. You have covered many things, especially the chemical vapor deposition and Longmire bloget technique, and many things you have covered. And I hope that if the MSc students are available, definitely they would have understood many thing about the nanomaterial preparation. I think we can have one more talk. This is what I feel about the nanomaterials, and you have presented very well, and all those things are very good, and that's why on behalf of the KPA, Karnataka Physics Association, we thank you very much, sir. In this context, let us thank Dr. M.K. Raghavendra, who is actually providing the Zoom platform almost all Sundays. And we should thank even Dr. B.A. Kogali and also S.V. Raman and for making that YouTube preparation. So we thank on behalf of KPA to our KPA members and also the invitees. I think some invited persons are also available in this lecture.
But they are
Let
joining.
us thank them from KPA. And again, from KPA, we thank all those persons who have attended. Thank you very much, sir. Thank you for your nice presentation. Thank you.
Thank you. Thank you very much.
Thanks a lot. Thanks a lot. So we'll meet next week again at the same time. Thank you very much for participation. So now we are closing.
Okay.
Thank you, sir. Thank you.
Recording stopped.